seen previously that if we were to put some solid zinc into a solution of copper 2 sulfate, that there would be a reaction, a redox reaction, in which zinc gives 2 electrons to that copper ion, and so the copper ion soon becomes metallic. It ends up having no charge. So that copper ion turns to copper solid, whereas that zinc, having lost 2 electrons, becomes zinc ion and dissolves into water. So if we were to put this zinc into a blue copper solution, that solution would lose its blue tint because that copper, which was providing that color, which was turning into solid. So we know that this reaction is spontaneous, and the reason might be said to be that zinc is more reactive than copper. Zinc is higher on the activity series for metals than copper is, and so zinc as a solid metal is more likely to react than copper. It can switch places with the copper, so that copper becomes solid instead of zinc. This reaction is spontaneous. Now, you can describe this reaction using the molecular equation. Zinc solid reacts with copper 2 sulfate solution to give copper solid and zinc sulfate solution. And you can write the complete ionic equation as provided, and then the net ionic equation. You can describe this net ionic equation using those redox reactions where zinc, you see, is losing those 2 electrons, it's being oxidized, and copper is gaining those 2 electrons, it's being reduced. We've seen all this before. But now, let's bring that back into describing batteries. Why not, instead of just allowing that spontaneous reaction to occur, this reaction which releases free energy has a negative delta G, why not harness that free energy so that you can do work with it? Why just waste this ability to do work? You can harness the free energy of this reaction by having the reaction occur in 2 separate cells. So we have one which has zinc dissolved in the solution, and we have one which has copper dissolved in solution. The same reaction can occur, but this time those reactants really are kind of separated, and they're only connected by a wire. You can place a zinc anode, so a zinc electrode, and in this case it'll be an anode, into a solution of zinc sulfate. And you can place a copper electrode, in this case a copper cathode, into a solution of copper 2 sulfate. Now, we've seen previously that zinc will become oxidized. It will lose 2 electrons. That spontaneously occurs while copper is reduced. But this time, though the zinc loses those 2 electrons, in order to make their way to the copper, they have to travel through this wire. You can see that zinc, it is still turning into zinc ion. Zinc is dissolving from this anode and releasing those 2 electrons. They're flowing towards the copper electrode, and those electrons, they can come into contact with copper in solution, and the copper can then be deposited onto the copper cathode. What happens to the masses of these electrodes? Well, the zinc electrode lost some of that solid zinc, so it will decrease in mass, and the copper, it had some copper ion which was in solution deposited onto it, so it will gain mass. Now this reaction is occurring, and electrons are flowing through, and we can see that they can actually power things. For example, the electrons, while they flow through, can flow through a light bulb as well and create light. Some of the energy of this reaction can be harnessed to create that light. Now, a couple things here. What happens if you continually build up the concentration of these positive zinc ions in solution, while you still keep the number of sulfate, negatively charged ions, constant? this solution would become increasingly positive, but having more positive than negative charge build up, this would start decreasing the rate that the reaction occurs and make the reaction less spontaneous. But we have a salt bridge here where here chloride, which is negative, can flow into that solution to neutralize any of that positive charge. Similarly over here, where we were losing that positive copper ion, it was becoming deposited. The negative charge was building up, but potassium ions, which are positive, can flow into that solution from the salt bridge and neutralize some of that buildup of negative charge. Now, we call this this electrode from which two electrons are flowing the anode. This is often represented by a negative charge because it's relatively negative when we have this excess of electrons. Those electrons will flow towards the positive cathode. Now, you should be able to recognize that at the anode, compounds are oxidized. Please note that anode starts with a vowel and oxidized starts with a vowel. You can also see here that at the cathode, compounds or elements are reduced. These both start with a consonant. So zinc is oxidized as it loses 2 electrons, and copper is reduced as it gains those 2 electrons. So we can describe the processes in this overall cell by describing the reactions here. We have, here's one of our half reactions. We show zinc as being oxidized, it's losing 2 electrons. And we can show that copper is being reduced, it's gaining 2 electrons. And that oxidation occurs at the anode, and that reduction occurs at the cathode. Now, the overall reaction, overall net ionic equation, is zinc is reacting with copper ion to give zinc ion and copper 2. But we can describe this overall cell using a cell diagram, which is showing first what's on the anode side. So first we write what metal usually is at the anode. We have zinc at the anode solid, and that's turning into zinc ion in solution. And let's say that we have a 1 molar concentration of zinc ion. That is, we're at standard conditions if we also have 25 degrees Celsius. Now, this anode and its solution are separated by a salt bridge, which is represented by these double bars. And then at the right we have our cathode, and right by that cathode we have a solution of copper ions, which is also in 1 molar concentration. So this is our cell diagram. We have the anode on the left and cathode on the right. Now this reaction is spontaneous, as we mentioned. Just as a spontaneous reaction has a decrease in Gibbs free energy. So the difference between pure reactants and pure products in free energy, recall, is delta G. Here we have a negative delta G. That should make our reaction spontaneous. We know that the reaction will go somewhat more into having products than reactants. So we have a spontaneous reaction which is described by G, the free energy, but we can also describe it in terms of electrical potential energy. Our reactants have higher electrical potential energy than the products. And so, again, the reaction proceeds to the right, and we can see that there's going to be a release of that potential energy, which is used to drive I guess, non-spontaneous processes, such as that light being released from the light bulb. Now, we can describe this electrical potential energy difference between our compounds by voltage of our cell. I guess another way of describing this reaction, instead of just saying that that our copper has higher electrical potential energy, our copper ion has higher electrical potential energy than zinc ion, we can also describe just the electrical potential energy of the electrons. We know that in general, we have water at some high altitude, and it's high in potential energy, and it will spontaneously flow down to a lower altitude and a lower potential energy. Spontaneously, energy is released as that water is falling. You could harness that energy by maybe getting, I guess, some kind of turbine. I guess, what do they have? They had water mills or something which harness that energy to grind grain. You can harness that energy now using hydroelectric dams. But you can also harness the energy of the difference in the potential energy of your electrons. Electrons are higher in potential energy at the anode and lower in potential energy at the cathode. And electrons will spontaneously flow from the high potential energy to the low potential energy. Spontaneously flow from the anode to the cathode. And you can harness that energy by using a light bulb, say, or further transferring that through wires to, say, make coffee, etc., etc. Now, you can describe the amount of energy, potential energy difference, by voltage. Voltage is, actually 1 volt is the number of joules for 1 coulomb of electrons to flow. And I'll remind you that a coulomb is the charge of 1.60 times 10 to the 19 electrons. So this is affected by, I guess the amount of energy that's released by a battery is dependent upon both the voltage, so the potential energy difference between the anode and cathode, and how many electrons flow. Now we can describe the potential energy difference in a cell by the cell voltage, which is described in volts or voltage, and similarly also cell potential and electromotive force, EMF. In our previous case, we saw that with a copper and zinc cell, the standard E cell at 25 degrees Celsius and having 1 molar concentrations of those things, we had 1.10 volts. Thanks for watching, guys.